This will be my solutions for quiz 8 on, let's see, Z transforms, pole zero plots, and filtering. So let's get to it. This will be the Tuesday Harley section. So you have pole zero plots for H1, H2, and H3. And as is filter one best described by a low pass, high pass, band pass, or stop band filter. Briefly describe why. So you start with filter one here. And the easiest way is to use your pole zero plot to guide your drawing of a magnitude response graph. So if you imagine this, it's going to lower in magnitude near pi/2 at these two zeros. So it's going to start out with a high magnitude and fall down near pi/2, not necessarily pi/2, but the first zero, go down, up a bit in between zeros, down, then back up and to the right. And then the symmetrical part is like this. If you want to label your axes, this is pi/2. Pi at the tail end, 0, negative pi/2, and negative pi. And this is an easy stop band because you're getting cut off at where you draw it near pi/2. And that's your answer. Next is filter 2, an FIR filter or an IR filter. Briefly describe why. And this is an instant answer of being an IR filter. How you know this is actually the locations of the poles. This is what you need to pay attention to. And your reason that you need to give is an IR filter because the poles are not at the origin. So there's really only two cases that you need to consider. Is it not at the origin, or is it not trivially at infinity? In this case, because the poles are not at the origin, that means that if you thought about writing the difference equation or the factorization, you're going to see that there's recursive elements in Y, and it's going to be an infinitely long sequence. So really, the easy answer, the poles are not at the origin. You're done. Next, for filter 3, identify the impulse response H of n. So you look at this, and there's a 0 at the origin, and there's a pole at 0.8. This should guide your way of writing H of z. That's all the information you know at this point. So the numerator must be z, because it's at the origin, the 0, and the pole must be at 0.8. Now you need to convert this into some form like z to the -1 so that you can do an inverse z transform. So if you imagine multiply this by z -1 over z -1, then what you'll get is 1 over 1 minus 0.8 z to the -1. And this is a very familiar inverse z transform impulse response of the form 0.8 to the n. Maybe I write like this, U of n. And for some reason you didn't know about that. It's it's pretty common throughout this class. At this point, it would be right here on this in the table. Next, you have the question, identify which filtered pole zero plot best matches with each magnitude response below. I sort of hinted at magnitude response B already, and the point I'm making is that there's these zeros near pi/2, which is exactly filter 1. So that's an easy answer. And you can sort of see the similarity between how I drew this magnitude response B and my quick sketch earlier in part A. Let's see, if you want to do a different one, let's say you want to do magnitude response C. What you need to get at is that its magnitude increases towards the higher frequencies near pi. So you want to see poles near pi, and that would be filter 2. By process of elimination, you would get that this is filter 3. But let's say that you just want to reason it out. You want to have a pole near the origin so that not pole near the origin. You want to have a pole on the 0 frequencies so that near the 0 frequencies, its value is going higher. So that will be exactly filter 3 because its pole is at 0.8. So that's the rationale for thinking about how to match these together. Next, determine the z transform of H of n. simplified to this form, given this H of n here. Okay, so the second term is an easy Z transform. The first one is the more unfamiliar one. So you probably want to look for the formula sheet for this one. And that will be this one right. Just choose a random color. It'll be this one right here. And remember, A equals 0.75. Okay, so let's just write it out. H of Z, take its inverse, take its Z transform component wise. So this would be 0.75 Z to the -1 over 1 minus 0.75 Z to the -1 squared. And then the easy one is 1 over the second term, 1 over 1 minus 0.75 Z to the -1. And I need to simplify it as much as I can. So I'm just going to do the common denominators. 1 over 1 minus 0.75 Z to the -1. What you'll see from this is that there's cancellation on this term, and this term. So what you're going to get is 1 over the remaining term, 1 over 1 minus 0.75 Z to the -1 squared. And I still need each individual term on the denominator expanded out. So this would be 1 over 1 minus 2 times 0.75, 1.5 Z to the -1 plus whatever 0.75 squared is, Z to the -2. Okay, that's actually your answer right there, and you're done. Next is the filter FIR or an IR filter. Briefly describe why. Again, your answer is instantly IIR. And the reason that you need to give is because the pole is not at the origin. The pole, as you discovered, based on this expression here, the pole is at P equals 0.75, and you're done. Is the filter best described by a low pass, high pass, band pass, or stop band filter? Briefly describe why. When you do these, you want to draw your pole zero plot and its meaning in terms of the magnitude response. So if you start, you know its pole is initially at P equals 0.75. Where is it 0? Well, you can sort of interpret zeros at this point earlier, because if you write this as Z squared over Z squared, you'll get this trivial 0 at the origin. So you have this. And the meaning of this pole zero plot, if you sketch the magnitude response, is that this pole at 0.75 is going to increase its magnitude response at the lower frequencies near 0. So this is a classical low pass filter. Lastly, is the system stable? Briefly describe why. This is an instant answer of being true. How do you know this? You just need to check if the poles are less than 1. If the poles are inside the unit circle, yes, then that would mean it is stable. In this case, your pole is P equals 0.75. The other case, obviously, is if your check was P greater than equal to 1. If so, this would be unstable. And that'll be all. Your answer is it's stable.